All right, this is day 2 of graph theory. So last time we talked about some basic definitions, we talked about what a graph is, and this time we are talking mostly about more definitions. So there's just a few other ideas that we need to get across before we can really dive into various properties that these graphs have. So a couple more definitions first. The first of which is that we'll use this term a lot just because it's convenient. We'll say that two vertices are adjacent if there's an edge between them. So we have our whole graph. There are often vertices that don't have an edge between them, so those two are not adjacent. But if there is an edge, we say that they are adjacent. Making this distinction is going to make our lives easier moving forward. And then our second definition here is that a graph is bipartite if it has this property. All right, and so this property is that it's possible to divide the vertices up into two separate groups. And in each group, no two vertices are adjacent. So let's take a look at what that looks like. Here are two graphs, each of which happens to be bipartite. So the way I usually think about this is I use colors, and I say that if it's possible to color the vertices so that no two vertices of the same color share an edge, no two vertices of the same color are adjacent, then we are in fact bipartite. So here I've used blue and orange, and you'll notice that no two blue vertices share an edge, and no two orange vertices share an edge. Once we have that, once we've colored all of the vertices and it still has this property, that's enough to say that our graph is bipartite. So it isn't always the case that the vertices are clustered in sort of this nice way like that, but if it is possible to do this coloring, then it is in fact bipartite. So again, we have another way of taking a graph and coloring the vertices to see that this property holds. We'll actually use coloring a lot when working with graph theory. We'll occasionally color vertices, we'll color edges, and this is going to let us prove things moving forward. All right. Here's a graph that is not bipartite. And one way to see that is that, well, if we started doing this coloring process, let's say that this vertex is blue, well, then because it's adjacent to the vertex down here, this one must be a different color. So this vertex must be orange. This lower left is adjacent to the bottom right, and therefore the bottom right has to be a different color than orange, but it also has to be a different color than blue, and we're only using two colors. Therefore this graph is not bipartite. So there's a number of graphs that are common enough or simple enough or follow basic rules enough that we want to give them names. And the first of which is going to be the complete graph on n vertices. So by complete, we mean that it has all of the edges that it possibly could. So if we have two vertices, well, there's only one edge that's possible. That gives us K2, or the complete graph on two vertices. K3 is the graph that has these three vertices, and again has all possible edges. This pattern continues. We could have K1000 would be 1,000 vertices, and between any pair of vertices is an edge. Using a similar notation, we'll say that Kn, m is the complete bipartite graph on n and m vertices. To see what I mean, here's an example. So here is K23. So this is the complete bipartite graph on 2 and 3 vertices. So what we want is this graph to be bipartite, so the group of 2 and group of 3 vertices cannot have edges between them. We can't possibly have an edge like that or like that. However, we want edges everywhere else. So if I start drawing edges, this, for example, is certainly a bipartite graph. However, it's not a complete bipartite graph until we have all possible edges drawn. So now I've drawn all of the edges that I can in this graph while maintaining the fact that it's bipartite. If I drew in another edge, it's not bipartite, so I'm not going to do that. So for any given choices of n and m, we can specify, or this is specifying, a particular graph. A couple more named graphs that we have. We use Cn to talk about the cycle on n vertices. So a cycle is just a loop. If we have 3 vertices, this is what a cycle on 3 vertices looks like, a cycle on 6 vertices, etc. And lastly, we use Pn to talk about a path. And notationally, I find this incredibly frustrating that this is the convention that's adopted, but we typically say that Pn is the path on n plus 1 vertices. So this particular graph is P4, largely because it has 4 edges, but for other conventions, for example, our complete graph, we're talking about numbers of vertices, so why this is the convention, I'm not entirely sure. I certainly won't ever try to trip you up with this distinction. I'll try to always make it clear that I'm looking for the path on a certain number of vertices, but just so you know, if you're reading some other context, it's certainly possible that it might be referred to in this way, and just be aware of potential confusion there. And then our last definition for the day, a tree is a connected graph that has no cycles in it. So here's an example of a tree. We have a certain number of vertices, but nowhere is there a closed loop. So remember, cycles are these loops where you start at one of the nodes, and if you're walking along the graph, you go for a walk and then end up back where you started. This is a cycle. A tree is something that doesn't have cycles. It's a connected graph that doesn't have cycles. So common examples of applications of trees include things like decision trees. Maybe you start at a certain point and then you decide to do one thing or the other, and then after you've done those, you're going to do some other actions. Other examples include things like family trees. You start off with you as sort of the base point, and your two parents and their two parents, and etc. And here we have, again, a tree because there aren't any loops, there aren't any closed paths in this picture. So that was a lot of definitions, and I will share with you a compiled list of these definitions just in case you forget any. And I apologize that this video sort of is mostly about, hey, here are all these just new definitions that we're throwing at you. Most of the interesting part of graph theory, I think, is sort of best discovered rather than told. That said, I do want to walk through what a proof using this material should look like. So I'll be asking you to write sort of several proofs about ideas that you're working out for yourselves in your groups. But here's one to get the ball rolling. So here's the theorem. A graph is a tree if and only if between every pair of points is a unique path. And so because we have this if and only if statement, we'll need to show this in both directions. We'll need to show that if a graph is a tree, then between each 2 points is a unique path. And we'll also need to say that if we have some graph that has this property, between every pair of points is a unique path, then the graph must be a tree. So we need to show both directions. First off, let's wrap our head around what we're talking about with a picture. So here is the tree that I used before, and notice that if we pick any 2 points, not only is there a path, but there is only one path. The only way to get from A to B is by taking this edge, then this edge, then this edge. As I said, we'll need to show both directions, but let's start off with the forward direction, meaning that we want to show that if a graph is a tree, then every pair of points has a unique path connecting them. Right. So let's assume that G is a tree. So let's take our graph, let's give it a name. Let's say that it is a tree. And then let's pick 2 points, and we're going to show that there is a path connecting those 2 points, a unique path connecting those 2 points. So X and Y are our arbitrarily chosen points. They are distinct vertices. If there are no distinct vertices, if there's only one vertex, then by default it's already a tree, so we're good. If we have more than one, let's take different vertices, and we will show that there is a unique path connecting these 2 vertices. That statement in itself has multiple pieces to it. We need to show that a path exists and that there's only one path. Thankfully, that first part is fairly straightforward. We know that a path exists because in the definition of a tree, we assumed that the graph was connected. So when we assumed that G was a tree, we assumed that G was connected, which means that between any 2 vertices, we have a path. So that one's easy. To show that that path is unique requires a tiny bit more work. We'll use a proof by contradiction. So to show that this path between x and y is unique, let's assume that it's not. Let's assume that if we've got our vertex x and our vertex y, that there are different paths that can get from x to y. We can't quite say, oh, just because there are multiple paths, there must be a cycle. We need to justify that a little bit more. We need to say that, hey, this particular thing that I'm talking about is the cycle. We need to find the cycle. And the issue is that it might not be that, well, there's a path connecting x and y, and there's another path connecting x and y, and collectively that forms the cycle. It could be that the two paths start off the same, and it's only after certain ways that they split off. So the cycle that we're looking for in this picture is this particular cycle. So in our proof, we need to sort of specify how we find that. So here's how we specify that. Here's how we say where the cycle is in this hypothetical graph. So we say that because there are at least two different paths, well, the paths might start off the same, but at some point they split off. But at some point, the paths diverge. And let's call the vertex where that split first happens x prime. Right? So if we're going from x to y, one path starts off at x, gets to x prime and goes one way, and the other path starts off at x, gets to x prime and goes the other way. It's certainly possible for x and x prime to be the same vertex, but we're just giving a name to the place where that split first happens. Because these two paths each end up at the same place, then at some point they have to come back together. Again, that might not happen right at y, but we'll just give a name to wherever they do end up coming back together. So x prime and y prime are just the vertices where the split starts and ends. So that is where our cycle is. Between x prime and y prime, if we take one path there and another path back, we've formed a cycle. However, we assumed that G was a tree. So when we supposed that the path was not unique, that was the only assumption that we've made since then. Well, assuming that the path is not unique means that G must not be a tree. Therefore, if G is a tree, then the path must be unique. By contradiction, we have shown that the path between x and y must be unique. Therefore, we've shown the forward direction for this theorem. To show the left implication, the other direction of this theorem, we want to take a graph and assume that it has the property that, given any 2 points, there is a unique path connecting them. Right? Using that assumption, we want to show that this graph must be a tree. To show that it's a tree, we need two things. We need to show that it's connected, and we need to show that it has no cycles. All right. For the first part, showing that it's connected is really just pointing out that, hey, we've already said that every two vertices are connected, so we're good. To show that it has no cycles, again, we'll use a proof by contradiction. So suppose that G does have a cycle. We have this property that every pair of vertices is connected by a unique path, and we're assuming that G has a cycle. We'll use those two in conjunction to find a contradiction. So we're just assuming that G has a cycle. Here is a picture just to have an idea of what we're talking about. Here is a graph with a cycle in it. To point out the contradiction, let's take any two vertices that are in this cycle. I'm going to use this one and this one. Now, the contradiction is that, well, we already assumed that every pair of vertices is connected by a unique path. So since there are distinct paths from x to y, we are contradicting our assumption. We started off assuming that there was only one path from x to y. So since we have a contradiction, that must mean that our assumption was wrong and that G can't have a cycle. If G is connected and doesn't have a cycle, then it's a tree. So therefore, G is a tree, QED. So again, the point of this was to go through a proof of a statement about graph theory in all its glory, and I certainly wouldn't expect you to write this much or be this verbose in your group work in class, but this is the type of proof that you should be able to write given enough time and effort dedicated to it.